Welcome to Know-How. In this video, we will look at a RC high-pass filter. RC high-pass filter is drawn like this. So where you have a capacitor and then a resistor, both are in series, and we take the output here, V out is here, and then Vn is here. So capacitance C and resistance R. So now if we write the transfer function for this one, so which is V out over Vn, so we will see that it would be R, which is the resistance of the output, divided by the total impedance from Vn to ground, which would be 1 over Sc, which is the reactance of the capacitor, plus R. So which can be further simplified to SCR plus 1 here and SCR in the numerator. So if you look at this, it looks as if it has, this is in the form of S tau over S tau plus 1. So it has a pole at 1 over CR, and then it has a 0. There is no plus term here, so there is nothing for the real part, so it has a 0 at 0. So you can imagine it to have a 0 at 0 and pole at 1 over CR. So which you can write it as, if you can simplify this further to get the magnitude and the phase, we can write this as, we can take the SCR, so let me write this first, SCR over SCR plus 1. So we divide both the numerator and the denominator with SCR, so we get 1 over 1 plus 1 over SCR. So which can also be written as 1 over 1 plus 1 over j omega CR, which can be simplified as 1 over 1 minus j, because j square is minus 1. So we know that j square is minus 1. So we use that and we get minus j over omega CR. So now from this we can get both the magnitude and the phase. So let's get the magnitude first from here, or we'll do both here. Magnitude, the magnitude is 1 over square root of, the real part is 1 square, plus the imaginary part is minus j over, or minus 1 by omega CR. So it will be 1 over omega square C square R square. And now if you write it in dB, in decibels, it would be 20 log to the base 10 1 over square root of 1 plus 1 over omega square C square R square. So let me put this. This is the magnitude in dB. So we got the magnitude in dB. Now let's try to get the phase from here. So we know this is the 1 over 1 minus j omega CR. So phase would be, because it's in the denominator, you put a minus first, and then you put tan inverse the imaginary part over the real part. Now the imaginary part is minus 1 over omega CR, and then divided by the real part is 1. So which would be tan inverse minus x is minus tan x, so the minus would come out and become total plus here, tan inverse 1 over omega CR. So this is the phase theta. So now let's put a box around this. So this is the phase. So now if you can calculate the table for that. Now again, when you look at now to calculate the 3 dB frequency, so we look at this again. So we look at this. So here for 3 dB frequency, the magnitude should be 1 over, the magnitude should be 1 over square root of 2. To achieve this one, what happens is omega square c square r square should be equal to 1, because this is the magnitude we calculated here. So our omega cr is equal to 1, or omega is equal to 1 over cr, and omega is 2 pi f. So f3 dB, this you can call it omega naught, f3 dB equal to 1 over 2 pi cr. So this is how we get the 3 dB frequency for this. So we got the magnitude in dB here, and then we got the phase in degrees, and we got the f3 dB frequency. Now if you see how the bode plot for this will look, so now if you draw magnitude with respect to frequency, so you have omega naught here, which is the frequency, or f3 dB. At this point we know that it's minus 3 dB. And then after that it increases and goes to 0. So it is 0 dB here at higher frequencies. So if you actually take an example and calculate, you will get this for this high pass filter. And now from here on it keeps falling at minus 20 dB per decade. So minus 20 dB, or basically it increases. If you look at this way, it's actually 20 dB. If you look at it from the higher frequency to lower, it's 20 dB per decade. So the change is 20 dB per decade here. So this is how the magnitude plot of a high pass filter will look. So now you can, if you try to make it an approximation, you do it like this. So at 3 dB frequency you start making the transition to my 20 dB per decade. So but actually here it is minus 3 dB. Now if you plot the phase for this with respect to frequency, now we got omega naught, and then we got 10 times omega naught here, and then we got 0.1 times omega naught here. So now at omega naught again you will get a 45 degrees, but this will be plus 45 degrees here for the high pass filter. And then at the lower frequencies, which is 0.1 omega naught, at 0.1 omega naught you can approximate it to 0, and then at 10 omega naught you can approximate it to plus 90 degrees. We will take an example later and look at this. So the phase, you draw it like this. So you have 45 degrees, but really in reality the phase plot would look like this. So here it would be like 5 degrees. It will pass through 45 and it will be 84 here, and then here it would be approximately 6 degrees. So this is how the phase plot would look like for a high pass filter. So in a high pass filter, the output will be leading the input by a phase of 90 degrees once you have reached a certain frequency.